Namaskar. Welcome to Prakash on Basics. I am Prakash Zog and I have been talking on light recently. We are now going to look into refraction, which is the second major property of light, and that's one of the properties that we use very extensively all around us. It's more important because that's the one which helps us to see things around. Our vision is based on refraction. What is it? When light from one transparent medium enters another transparent medium coming at an angle, then this light bends. This is basically what refraction is. But there are two more changes. The speed of light on entering the different medium also changes, and its wavelength also undergoes a change. If you take a stick and put it or immerse it in water, suppose I take an object like this, put it in water, then at the boundary this would tend to bend, and we see it very often. When you stand next to or put a pen in a glass of water, and you would see this happening. The rays of the light are to be noticed from the inner medium that are coming to our eye, so the stick seems to bend upwards when it is immersed inside. For every medium pair, every transparent medium pair, this amount of change that takes place is fixed in wavelength, in the angle that it changes, and the speed, of course. And if you take this ratio tends to remain constant, and this is the one that is known as refractive index. There is something known as absolute refractive index, which is defined for vacuum, but air is as good as vacuum for all practical purposes, because the speed of light is practically the same in air, 3 lakh kilometers per second, as I told you. When it enters glass, this speed becomes 2 lakh kilometers per second, 2 into 10 raised to 8 meters per second. So if I take the ratio of these two, then that ratio is 3 into 10 raised to 8 divided by 2 into 10 raised to 8, which will work out to be 3 by 2, which is 1.5. So the refractive index of glass is 3 by 2. And if I talk of the refractive index of water, it is 4 by 3. So if the speed of light had been 4 in air, it would become 3 in water. So if you take that calculation into account, it will work out to be 2.25 into 10 raised to 8 meters per second. Let us forget the numbers, it is the ratio that matters. So naturally, if I have light of wavelength of a certain value entering from air into water, the product of velocity is the product of frequency and wavelength, and frequency is a measure of the amount of energy. So the energy is not going to change, the speed is going to become less, the velocity is going to become less, so naturally the wavelength will also become less. So if the frequency of light in air is 4000 angstroms, on entering water it will become 3000 angstrom. Similar change would take place even in case of glass. So depending upon the two media that are present, the wavelength, the speed and the angle that is made are all different. This is actually given by a particular law which is known as Snell's law. But then there are other laws of refraction also, and they are very similar to the laws of reflection that I talked of last time. We need not really know all these laws precisely, but if you understand these laws, then you can understand how the properties work or why a certain thing happens in case of light. Let me remind you of the laws. I will just tell you what they are. Suppose you take a boundary. This is the lower part is let us say glass, and the upper part is air. So, if a ray of light comes like this, instead of going like this, it will bend inwards. What is the reference? The reference is the vertical, or what is known as the normal. So, on entering a dense medium, the ray will bend towards the normal. On the other hand, if you put a mirror here and the ray reverses, then exactly, which is known as reversibility of light, the same thing would happen, but in the reverse order. So, when the ray from a dense medium enters a rare medium, it will bend away from the normal. There is an angle. With the vertical, the angle is known as angle of incidence, and the angle inside is angle of refraction. So, in a rare medium, the angle is greater, and in the dense medium, the angle becomes smaller. If the ray is coming from this side, this is angle of incidence and this is angle of refraction. If the ray is going in the opposite direction, this is angle of incidence, that is angle of refraction. In rare, the angle is large, in dense, the angle is small. But what about the ratio? The ratio is talked of in terms of a mathematical relation, which is known as sine of angle of I divided by sine of angle of R is constant, and that is the refractive index, and that is that 3 by 2 or 4 by 3 for water that I mentioned. Of course, the light rays can't come like this and go like this. They have to be on the either sides of the normal, and the ray can't come like this and go suddenly this side. All of them have to remain in the same plane. So, these are the additional laws that are a part and parcel of the process. So, these are the laws. How do you use them, and what do they make sense for us? One thing I have already pointed out, it is the frequency that remains the same. It is the wavelength and the velocity or speed that will change. Now, the next logical step. Think of light coming from a dense medium going into the rare medium. So, if it comes like this, it is going to bend like this and go out. So, if it comes at a bigger angle, the angle here is going to change more. For a certain value from inside, the angle outside becomes 90 degrees. The angle for which this happens from inside is known as the critical angle, and that is very important because it gives rise to a completely different but a very important phenomenon that still depends upon refraction, and that is known as total internal reflection. I will go back. The ray comes from here at such an angle that instead of going out, it turns back into the same medium, and then this surface starts acting as a reflector, and that is total internal reflection. Depending upon the medium that is there on either side, the angle would be different. For water, this angle is 48 degrees, anything more than 48 and it will turn back in. For glass, it is around 38 degrees because its refractive index is different, and for diamond, whose refractive index is 2.41, taken as 2.4, but around 2.41, 2.42. For diamond, this angle is 23 degrees, that is pretty small. So, even at a slightly greater angle, and the light will turn back in, and this total internal reflection gives rise to a number of phenomena that we use very often. It is used in I just talked of diamond. If you take a sphere of diamond and a glass sphere, they are practically identical. There is practically no difference at all. But then diamonds sparkle. And why do they sparkle? Because they are faceted. That means they are given cuts, and these cuts, princess cut and so many others, that is a part of crystal structure, not today. Um, so the cuts are designed in this manner that whenever light falls on the top, it goes inside, it gets totally internally reflected and comes back and comes out from a different facet, and so naturally the diamond seems to sparkle. So the sparkling phenomenon is because of the total internal reflection, which is based on the refraction that is taking place inside, and that's the reason the diamonds sparkle. But then there are more important uses also, and the next one, which is equally important, is what is known as optical fibers. Long back I had mentioned that optical fibers are used for communication and so forth, when we talked of radios and so many things, TVs and radios and so forth. What you do is you cause total internal reflection and restrict light to a transparent medium itself, but it can't happen with just one medium. So what they do is they take two very thin, transparent but different refractive index materials, one inside the other. When light enters the inner one, it gets totally internally reflected and continues along the same tube. So this system is typically referred to as a wave guide, because it guides the wave along its path. If by chance the ray comes out due to refraction, by the time it comes out, its angle is further increased. So naturally it hits the next boundary and goes back in again and remains inside. So if the tube is bent, then the light ray will also travel along the same path and will come out of the other end. So I could have light we always say travels in a straight line. So it can't travel from one room into the other, bend around. But if you put it through such a tube, the light would then go through. If you put it through an optical fiber, I can't do it with an ordinary glass tube. It doesn't work because the angle doesn't match. So the tube has to be extremely small and very thin. So what you do is, now instead of one tube, you take hundreds of tubes and make a bundle out of it, and that's the optical fiber that we talk of. And then if you put light from one side through these 1000 very thin glass tubes, they would come out of the other end and you would see the same light again and get the same image once more. So bending light is not just the only application. There is far more important thing that can be put to use. One, of course, is it can carry information, and that's how light lasers, when we talk of that, I will come to that. But in medicine, it is used in terms of some terms that you must have heard: laparoscopy, endoscopy. Mechanics uses a boroscope and so forth. What are all these? These are techniques that have been developed to aid illuminating areas that are not directly accessible. Suppose there is a machine, a big constructed machine, and there is a very small screw that I have removed, and inside something is wrong. I don't know what is wrong, so I can't disassemble the whole machine. So what I do is I put an optical fiber right through, illuminate it, because through 2 or 3 of them I put light, and the reflected light comes out of the remaining ones, and I attach a camera on this side and view what it is. This is known as a boroscope. So I can see what is happening inside, and if the machine is working, I can find out what is really wrong without really disassembling the whole thing. And God has made a far more complex machine, the human body. So if I have to see something inside, if there is a blockage, I can't just open my heart and say, okay, there is a blockage here, I'll close it down, I'll remove it next time. That doesn't work. And I'll have to go through such a big surgery just to see whether there is a blockage or not. Or if there is a kidney stone, the stone is so much, but then I have to cut 3 inches and go inside and cut everything in between and then pull that stone out. Why do all that when I can use another technique? What I do is I use an optical fiber, and along with it I now have micro tools. So it is possible to crush that stone inside, or illuminate it by using 2 more light sources, find out how big it is, hold it with a set of pincers which are attached to the same probe, and pull it out. So, all this is possible through a laparoscope, and that is used as I said, for kidney stones or some similar problems in our intestines and so forth. All these endoscopies, so you send it through your vein and see if there are blockages and find out how and where these blockages are and so forth. So, all that testing is done by using refraction, which results in total internal reflection in extremely thin, narrow capillary like structures, which are known as optical fibers. There's one more use. Remember last time I was talking of periscopes, and I mentioned that you have a set of mirrors, and if you are below water you could see what is on the surface of the water by using it through a submarine. It's a pipe, water would go through, so you seal it up, but the pressures could destroy everything and the glass would not really work. You need a very good insulator, so water preventer. So what you do is you use a different technique. There is a second thing. If you use a binocular, I'm going to come to the those applications next time, but let me remind you that many times you can't really use mirrors. So what you do is you use something else which uses refraction. So you use a prism designed in a particular manner which acts like a mirror, and the image goes here and goes back, so that you can increase the total length through which the image formation takes place, and the binocular can become much smaller in size than a big long tube extending all the way up to infinity. So that's one application by using total internal reflection. And my friends who use cameras must have heard of Pentax cameras. What's a Pentax camera? The Pentax is, Penta is 5. So there is a special prism inside which has 5 sides, and this pentaprism is used to form the necessary images and show is used in the camera to get an image of the actual object that is being photographed. Nowadays, of course, there is a more sophisticated technique of using extremely good reflecting surfaces, and the mirror goes up, but there could be a slight time delay. To prevent all that, a printer prism was used, and then Ashai Pentax and other cameras were the ones that use this particular technique. So that's again total internal reflection. So in many situations, this total internal reflection is used. These are just some of the applications. Now, what else do we see as far as refraction is concerned? We see one more major phenomenon in nature, which is known as mirages. I'll point out 2 things. One, you see it is always, when we studied this in school, they always showed a desert in which a palm tree was shown shifted somewhere else, or a camel was shown shifted somewhere else. Why the desert? Because at that time it was quite obvious that it is there that there is extremely hot sand, and air is in the form of layers, and each layer has a different refractive index, and so naturally light traveling through it will bend. So if light is supposed to come to you like this, it actually bends and comes like this. So instead of appearing to come from here, it appears to come from a different point, and so you see an object at a different location than the original location, and that's what a mirage is. And the layers are slightly dicey, moving around a little bit, so it looks like water. So this is more like you see a lake or a set of water somewhere, and so in Indian languages it is called as Mrugajal. It's the virtual water behind which mrugas or deer run till they get exhausted searching for water. Does that happen today also? Yes, of course. A slightly more complex situation, but if you are driving along a very hot afternoon and you look at the road, and if the road is empty and far away, if the road is a tar road, then you see the reflection of the vehicles on the tar road itself, because at a very large distance the tar road starts appearing like a glass film. All that is because of the total internal reflection in the variety of layers that are there in between, and it is these layers that are wobbly, so the image seen is also a little wobbly there, and that effect is the liquid is shaped. As soon as you come to the road, you find that there is no water there, because its action as a mirror disappears because the angle has changed. These such small angles are referred to as grazing angles, and it is this grazing angle that changes, and then that effect is gone. So that image formation is because of the heat and the variety of layers, and this happens even because of pressure. So as we go higher and higher in atmosphere, the layers have lower and lower pressure, and so the refractive indices are different, and that gives rise to one more phenomena that we see at night. That's also related to the same thing that we are talking of. Why do we see an image? Because light comes all the way along, a number of rays come and form an image in your on your retina and brain, something we will talk of next time. If it's the sun, the whole image is very bright, and so your eye tends to shut down. Moon is pretty big image. Planets, they are relatively closer, so they form a pretty good image of that particular planet, and you can see those morning stars and so forth, Venus and Mars and so forth. But what about stars? They seem to twinkle, 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 little star. Why twinkle? Because they are so far away that the net quantity of light that goes in your eye is extremely small. Just a few rays are reaching your eye, and they are coming through a number of layers. And when these layers get disturbed a little bit because of variety of reasons, the ray of light bends in a different direction and cannot reach your eye. For that instant, that star is not visible, and the next instant the layer comes back to its normal level and you start seeing the star once more. And so that twinkling effect that you see is because of that light reaching or not reaching your eye, because of its refraction through a number of layers that are not steady, and that is why you see such effects. Actually, you can see this effect at one more place. Suppose you take a tawa or a hot plate, and it becomes pretty hot, and the instant it becomes hot, all the layers of air on top of it start, because of convection currents, they start rising, and their densities are different, and the whole set of layers are mobile. So anything that is beyond that and you are looking at it, that image starts wobbling or is hazy or is distorted, and that is because of the refraction of light that is coming through. So bending of light because of all such things is because of this refraction. Let me remind you that gravity also can bend light. That's a completely different effect. We will talk of that sometime much later, not today. That's a part of gravitation. That's not today's job. So that's what happens. One more issue. Suppose I take a block of glass. Let the ray come from this side. So the instant it enters, it goes like this. The instant it comes out from here, it goes back parallel again to itself. So the original ray, same effect, reverse is happening here. So the ray goes parallel all the way through, but because of the thickness of glass, it has gone like this and like this. So it comes out parallel instead of coming like this. So there is a parallel shift because of the glass block in the ray of light that is going through. And if I change the shape of that glass block, then what happens? and that gives rise to two more major effects. If I give it a shape like this, what I get typically is referred to as a prism. A glass block of this particular shape is known as a prism, and this is known as the angle of the prism, the one that is there at the apex. These are the two faces on which the light is falling, and this is said to be the base. So if a ray comes like this and passes through a prism, it bends towards the base. That's the rule. Even if parallel set of rays come like this, they would bend towards the base. How much they will bend will obviously depend upon this angle and what is the material of this prism. So common sense will tell me that if I reverse this prism, then the parallel rays coming like this will go upwards instead of going downwards as they were there in this case. And that is something that we will use next time to interpret one more major application. There is one more issue in this itself, and that is the prism also causes splitting of light into its constituent colors, and that is known as dispersion. But that is a completely different phenomenon, and it has its own applications. We will spend some time understanding that too, because that is equally important, and that is how the rainbow forms and so many other things. But in all this process up to now, I have talked of two things. One, light bends. Second, its speed changes, it reduces. Question is why? And that answer is slightly difficult. It's more a part of scientific interpretation that is there. I'll go through it because that's an obvious question that would arise. I'm sure you will bear with me to grasp. It's a little tricky to understand, but it's not very difficult. I'll try and simplify it. Light has a particular speed in vacuum, which is 3 into 10 raised to 8. That means 3 lakh kilometers per second. And there is no other material in the vacuum, and so light travels at this particular speed. As far as air is concerned, it is practically the same. The 1 or 2 small digit shift, that's all. But whenever this light enters any dense medium, the medium is made out of a number of electrons, protons, neutrons and so forth. And this is an light, of course, as I told you long back, is electromagnetic radiation. That means an electric field and a magnetic field that is constantly changing. And if a charged particle is placed in it, it's going to start oscillating on its own because of this. Oscillating because it's going up and down, the field is changing up and down, so naturally the particle will go up and down. And if a charged particle is moving, oscillating, it will create its own electromagnetic field. The electrons will produce this field to a larger extent. Protons, which are 2000 times heavier, are going to move a little less. Neutrons will not have any effect. This is an extremely small effect and not noticeable under normal conditions at all, but it does take place. And there was a scientist called Lenz who said that in all such phenomena, to conserve energy, the direction of all such effects is reverse of the original, otherwise the energy doesn't get conserved. So you have two sets of waves, electromagnetic waves, and they are going to affect each other, so they superimpose on each other. In case of light, this is known as interference of light, and this superposition could be constructive or destructive. In this case, of course, since it has to oppose, it will be destructive. So the two waves together form what is known as a group wave, and that has a particular velocity of its own, and that group velocity is a little less than the original velocity at which the light has entered. So as long as the light is within the medium, it is slowed down. The instant it comes out of the medium, that effect is lost, so it goes back to its original speed, whatever it was. So that is the reason why light slows down. Actually, the density is a little more. If the refractive index is a little more, it implies that there are more free number of electrons, not free, but more number of electrons available which are capable of oscillating in this particular manner and resulting into more reduction in the speed of light and its corresponding effects. So, this is what happens. You might come across slightly different interpretations at some places, but they are not really valid. This is the one that is the correct one. Now, the next one. Why does it bend? It slowed down fine, but why should it bend? For that, it's associated to some extent with the geometry of, I told you that this is known as geometrical optics, the way in which light's interpretation can be carried out. But we can simplify things. Let us say there is a beam of parallel light. So, all the rays would reach at a particular distance at a particular instant if they are parallel, and this particular edge is known as a wavefront. And let us say this is a beam of light. I hope it is visible. A and B refer to the 2 points which represents the wavefront and the beam is coming like this. Let us say it comes and hits a glass surface like this. So, B comes in contact with this glass surface and the light starts entering into that medium at this point, but it is a different medium. So, the speed has become less, whereas this point A, the light will continue to travel at the same speed and reach this point till it reaches the other point here further down. When it touches and starts entering there, it will start traveling at the same speed as the previous one, and then there will be a new wavefront that will be formed. But think a little more carefully. Suppose instead of these points A and B, these are two wheels traveling at speeds. So, this wheel has slowed down because of its contact and entry into the different medium, while this is traveling at the same speed. So, what would happen? On touching and entering, this is like a car. If one wheel travels faster than the other, the car will turn towards the slower wheel, and that is exactly what happens, and the whole beam turns around and it enters into this medium. And had I talked of reverse, if it comes like this is slowed down while this one speeds up, and so the ray shifts in a different direction. So, this is how speed of light variation is going to result into the change in angle, and the amount of change in speed is going to decide on how much it will bend. But suppose it comes down vertically, there is no question of bending, but it has slowed down. The effect is that the size appears to become different, and so the bottom appears to be raised up than what is normal, and we see this phenomenon very often. Look at what happens when you are standing next to a swimming pool. Two things can be observed very clearly. If you look at the pool itself, you will realize that the bottom appears to be a little raised up. If the refractive index of water is 4/3, as I said, 1.333, which is 4/3, then if the depth of water is 4 feet, it will appear to be at a depth of only 3 feet. It will be raised up by about 1 foot. If you do not believe me, look at a person who is swimming in water and see how it looks. When he is outside, he seems to be normal, but within water, he seems to be a little odd. The reason is the depth up to which he is below water is above is normal. That is what you normally see. But within water, the whole thing appears to be compressed. So, if he is 4 feet below water, his torso or his legs are 4 feet below water, then they appear to be only 3 feet below water. So, his legs appear to be shortened and he looks distorted, but the instant he comes out of the water, the distortion is lost. You put a coin in water, you do anything of this sort, you look at a swimming pool at different depths, you will find this phenomenon very often, and this is how the images get distorted. In fact, this is one of the techniques that is taught in schools and colleges to measure using a microscope to measure the refractive index of water and different liquids and so forth. So, it is a very simple technique, but it is very interesting. There is a reverse phenomenon that I must also talk of. So when a fish, if you are going to hit a fish using a spear, the fish is not going to be where you are looking at from the top. So you have to aim at a different angle than the one at which the fish is. So the prongs used are usually with 3, so that if you are aiming with any of them, the lower one or the upper one of them is going to pierce through. Usually if you are used to it, you should be able to spear the fish accurately, and that's something that you can think of. So these are some of the effects of refraction of light that take place. But there is one more major effect, and that is converting not this prismatic shape but a curved shape, and that gives rise to lenses, and that's an independent area of its own. The most important one of them, of course, obviously, is our eye, where our eye lens produces the image resulting into vision. So that's what we need to understand, and that will be our next step. If you have liked whatever I have said, look up and see all these examples around you, and tell your friends about it. Like and subscribe to this channel, and we need to understand how our eyesight works and how lenses work, and that is something that we will do next time. So till we come back to that, Namaskar.